Hello all. Today we present our work on perceptual modeling of unconstrained road traffic scenarios with deep learning. So this would be the outline of our talk. First, we would like to discuss the motivation behind developing such systems, followed by a gentle introduction to advanced driver assistance systems with core functionalities that leads towards the L3, L4 levels of autonomy. Further, we would like to discuss various implementation approaches that we have tried in experimenting in developing the system towards real-time traffic flow modeling. Next, we will illustrate the results and discuss the evaluation metrics, and finally conclude our work by providing all the possible feature research directions and extensions. Significantly, to work on addressing the real-time challenges, we have chosen the road traffic scenarios that are chaotic, complex, heterogeneous, with less disciplined traffic in nature. As we can see from the table 1, the source from MORTH, that is Ministry of Road Transport Highways and Authorities, Government of India. Total number of road accidents recorded in the year 2017 were 4,64,910. So we can see that in the table from year 2005 till 2007, there is a gradual increase in the number of road traffic accidents, injured and also fatalities. Currently, recent years like 2018, total number of road accidents recorded were 4,67,044, leaving the persons fatalities as 1,51,417. With this motivation, we have come up with potential objectives in reducing and providing the driver safety. So our objectives include to develop a system that would efficiently monitor the real-time traffic flow along with vehicular detection and tracking of the objects. So also our developed system would enable the overall driver safety and also leads towards the L3 and L4 levels of autonomy. Before discussing some possible solutions, let's see what are the real-time road traffic challenges that were frequently observed. Possible challenges would be paved or unpaved road structures, unstructured chaotic road traffic, and diverse vehicle types like light motor vehicles, heavy motor vehicles like trucks, etc., and nature of the roads, which typically include gravel, earthen, muddy and slippery roads, and extreme curved lanes with improper or occluded lane markings and occluded signboards, and potholes with extreme in-depth depreciation areas and also broken dividers, road structures with broken surfaces and also complex and confusing roads. And all further, there is other concept called road traffic participants, which typically includes diverse and heterogeneous participants that follow less disciplined traffic. All these were commonly observed challenges that would lead to severe and critical road traffic challenges and accidents. One possible solution would be developing a system with advanced driver assistance system functionalities. Typically, these functionalities include lane keep assistance, driver distraction analysis, night vision assistance, addressing all the possible illumination challenges, obstacle detection with occluded and cluttered areas, pothole or broken divider detection, adaptive cruise control mechanism, and traffic sign detection. The main aim or objective behind introducing such advanced driver assistance systems is to provide and ensure the overall road safety with proper and efficient traffic management. The main idea or the goal is to make the vehicle understand its environment and have a complete visual perception about the immediate neighborhood and the external road traffic scenarios. And also, these systems will be capable of handling and addressing highly unstructured and diverse traffic scenarios with different and diverse driving patterns of the traffic participants. As part of this work for real-time traffic flow modeling, the main objective here is to develop an effective traffic monitoring systems that would enable in providing a solution towards achieving L3 or L4 levels of autonomy. As we can see in the figure 3, L3 and L4 levels of autonomy not only ensures the overall driver safety mechanisms but also leads towards the semi-autonomous solutions. So as part of this work, Two datasets were considered. One is the custom dataset, which is built from the scratch and providing the annotation for the ground truth information. The other is the dataset which is made publicly available in the Kaggle platform, IIT Madras V heterogeneous dataset. As part of implementation, we have used and experimented both traditional image processing and computer vision techniques, and we are going to discuss what are the drawbacks and limitations found in using the traditional mechanisms and what motivates us to choose the advanced deep learning based algorithms such as YOLO v3 and FastRCNN. We have collected our own custom dataset considering both the day and night driving scenarios. As part of this dataset, we have chosen 500 images for our dataset initially to work with, and for annotating the ground truth information of each and every object in the frame as shown in the figure 4, we have used VGG image annotator tool. Commonly, we have considered 4 frequent seen or observed classes in each and every frame in our dataset, which were person, car, bus and auto rickshaw. These are the classes even being considered in the other dataset that is provided by the Kaggle platform, with total of 2404 training samples and 216 test samples that were used for evaluation. And the annotation information is provided where initially it starts with the class category followed by the X, Y and width and height ground truth information. As shown in figure 5, it details the process flow for an efficient and dynamic real-time traffic monitoring systems. Typically, this involves application of background subtraction with morphological transformations on raw spatial data. Additionally, for better night vision enhancement, we have examined and utilized adaptive histogram equalization, gamma correction and contrast limited adaptive histogram equalization Clahe correction mechanisms for enhancing the contrast levels. The application of pre-processing methods on raw data includes centroid based tracking and also vehicle detection using contour detection. However, there are some limitations with application of traditional techniques with handcrafted features. This includes overlapping and cluttered contours with illumination reflections, resulting in poor or wrong detections sometimes. Hence, in order to avoid and overcome these limitations, an advanced deep learning based techniques such as single-staged and two-staged object detection architectures have been investigated thoroughly for application of real-time scenarios. Figure 6 and Figure 7 illustrates the detailed architecture overview of both YOLO v3 and FastRCNN algorithms. Considering the Figure 6, YOLO v3 is a single-staged object detection algorithm uses the variant of darknet with 53 layered network which has been trained on ImageNet. The YOLO v3 architecture comes up with a residual skip connections and upsampling. For the purpose of detection, an application of 1x1 detection kernels on feature maps of 3 different sizes at 3 different places in the network have been employed. For illustration, 13x13 layer is responsible for detecting the larger objects, whereas 52x52 layered detects the smaller objects, and finally 26x26 layer detects the medium objects. In YOLO v3 total it uses 9 anchor boxes, 3 for each scale. So object confidence and class predictions in YOLO v3 are predicted through logistic regression and also performs multi-level classification for objects detected in the image. YOLO v3 comes up with additional 53 layered stack that provides us 106 layered fully convolution underlying architecture. Similarly, the other architecture FastRCNN comes up with 3 major parts, namely convolution layers, regional proposal network and bounding boxes prediction. Convolution networks are generally composed of convolution layers, pooling layers and the last component that is fully connected layers. RPN, that is regional proposal network, is a small neural network sliding on the last feature map of the convolution layers and helps in predicting whether there is an object or not. Figure 8 shows the results as part of applying traditional image and computer vision techniques along with the tracking of vehicle in each and every frame. Whereas in figure 9, you can observe that in the right side the detections of each and every objects in considering both day and nighttime images, where YOLO with 500 image samples has achieved 78.5 mean average precision, and in figure 10 in the right hand you can see it has been showing the detection accuracy in both day and nighttime and also rainy images. FastRCNN have been tested and experimented on IIT Madras v-hetero dataset with backbone networks as Inception v2 and ResNet 101, achieving an overall MIP of 89.44%. To conclude our work, it investigates the use of deeper architectures for effective traffic flow modeling with vehicular detection in less disciplined traffic scenarios. Particularly, YOLO and FastRCNN have been employed for training and experimenting, where YOLO achieved an MAP score of 78.57 with IOU 0.5 threshold, whereas FastRCNN obtained 89 and 88% mean average precision with backbone networks as Inception v2 and ResNet, providing better detection accuracy. The possible extensions to this work would be developing a neural architecture search and CNN pruning mechanism to deploy an optimized model with a limited size for an deployable devices with low and less computational device like Arduino or Raspberry Pi and Jetson Nano, and also providing better accuracy, and also to work with weight agnostic design for real-time deployments and also handle affine transformations, improving the miscalibration rate of the predictions. Potentially, these changes would greatly benefit and enable reaching towards L3 or L4 levels of autonomy, providing for improved driver safety. As part of implementing this work, these are the core and important references that we have followed. We feel happy to answer the questions. Thank you.